So, we have seen that the way to generate any general fractal image is to use the collage theorem. And to recapitulate what the collage theorem essentially says, suppose there is a underlying space R2, space of two real numbers, and there is an object L in that, which means that in this space I have some kind of a object which is nothing but a compact subset of the R2 space. So, this is my starting point L. So, what is L? Is an element of the Hausdorff space okay. So, there is the underlying space R2 in which there is an element okay, and we will assume that there is a X D is a complete metric space. Then somehow we will construct some affine transformations transforms W1, W2, W3, so on and so forth. So that when W1 is applied not only on a point, but all the points on the set, it will produce a subset of this set. So, the whole set when operated on by the matrix or the affine transformation W1, then it gives a subset of the original set, W2 gives another subset of the original set, W3 gives another subset, so on and so forth, so that their union gives me back the whole. Suppose somehow we have been able to construct such affine transforms, then the collage theorem says that the Hausdorff distance between the original set L and union of the okay, here we have the original set L and L transformed by W1, L transformed by W2, L transformed by W3, all that taken union of, which means the transform thing, first one iterate, gives me, suppose this distance is suppose very small, which means that we have started from the set L and we have applied certain affine transformations on the set L, thereby we have got this union, another object. So, we can find the distance between original one and the transformed one, we find that that is small number epsilon. If that is so, then the theorem guarantees that if you calculate the distance between L and the attractor of that IFS, IFS is iterated function system, which means W1, W2, W3, Wn iterated a large number of times on any initial set will always converge on on something, the attractor, so that the distance between the original set and the attractor will be epsilon by 1 minus lambda, where lambda is the contractivity factor of this IFS. What does it say physically? What we will do? We have started with some image, we will somehow find the affine transformation, so that you get parts of that image, so that the union becomes as close as the original image as possible. That distance is our epsilon. If we do so, then we can forget about that set, forget about that initial L object, and then we can simply keep on iterating this iterated function system W1, W2, W3, W4 and all that on any initial image, and that will ultimately converge onto the set we want. This only says that when it converges, it cannot be said that it converges exactly on the set L. It can be said that it converges on some attractor A, and then the distance between the L and the attractor A will be small, that is all. Okay. If this epsilon is non-zero, then it will only be small, but you cannot say that it will be 0. If it is 0, then obviously this is 0. In that case, A becomes nothing but the L. Clear? So, with this, if you want to obtain the set of affine transformations, what we will need to do is to find out how can we transform the whole image to obtain a part of the image. For example, here on the computer screen there is an image. If you look at it, yes, in this image, by looking at it, it is a coral image. Can you find out which part you would like to obtain from the whole by looking at this image? See the whole. How to transform that? The problem is this: how to transform the whole so that you get a part of it. You see the part on the upper right side, is similar to the whole. So, that can be obtained by means of a affine transformation of the whole. The one that is at the middle, that is also a affine transformation of the whole, and the one that is at the lower left corner, this side, is also a affine transformation of the whole. So, I can simply by looking at it, I know that you would need 3 of the W's in order to produce this image. Clear? The next question is how to obtain the values in the affine transformation. That can be obtained by simple 6 by 6 matrix solution. What you will do? You will find out that a particular point maps to a particular point, another particular point maps to another particular point, and the third point maps to another point. The moment we have identified 3 points that map to 3 other points, you can easily write down the equations like so: x1 dashed y1 dashed is obtained as a, b, c, d x1 y1 plus e f. For each of these transformations, if you can find out this point maps to this point, we have x1 y1 mapping to x1 dashed y1 dashed. Therefore, if you substitute here, you get 2 equations, 6 unknowns. If you can identify 3 of these points, you get 6 equations, 6 unknowns, and that's enough. You can always find the numbers. Clear? So, in this case, I will give you the task of identifying these numbers for this particular fractal image. Okay. These for this particular fractal image. Let us go to another and take a look. In order to go back. Okay. Here in this case we have already treated this in the last class, right. Now, I wanted to bring back this because I wanted to show that the way the probabilities are assigned, I have already talked about the probabilities. In the random iteration algorithm, you need the probabilities in order to generate this fractal. In what way? In the random iteration algorithm, you will start from any point and then keep on applying the W1, W2, W3, W4 in sequence to those points, and the probability of having W1, the probability of having W2 and all that is assigned depending on some pre-assigned probability, right. So, you need the probabilities. So, here you can see that the 4 transformations land the image into 4 parts which are colored differently in this case, right, and the color, the region marked by red and the region marked by blue are almost the same size, while the region marked by green is much larger. So, in order to make sure that the similar number of points land there, so that the density of points are similar, you need to put a different probability in that part. Okay. So far so good, right? The point that I would make next is that such a immensely complicated image required only 24 numbers, right? Only 24 numbers to codify this image, which means that this allows a very large compression of the information contained in the image. What exactly did we use? We used the concept of self similarity. The fact that the part is similar to the whole, that is what we have used, right? And if the part is not similar to the whole, then we will not be successful in applying the same kind of algorithm. But if it is so, like here, you can apply this method and obtain a very large compression. So here we are talking about image compression really, and we are able to achieve a very large compression ratio. And the success obviously depends on the kind of self similarity that you have in a particular image. Let me go back to another image. Yeah. Here we have the Koch curve as the final image L. Can you identify what are the affine transformations necessary in order to obtain this, or how many would you need for that? How many of the W's would be needed? 3? No. See, can you see the image? Yeah. Here you have, can you see the cursor? Yes. So the whole range is from here to here, and out of that the whole thing, when affine transformation can be made into this small part, right? So that can be one affine transformation. The same thing, affinely transformed, that means same thing when you rotate a bit you get this part, same thing when you rotate a bit you get this part, same thing when you translate a bit you get this part, right? Union of them gives me back the whole set. So you need 4 affine transformations to generate this image. Clear? And you can easily write that. For writing the IFS for this particular image, you don't need the 6 by 6 matrix calculation. Why? Why don't you need? Because initially I have shown that this A, B, C, D, E, F can be represented as R1 cos theta and R2 sin theta, that kind of representation. That means the kind of shrinking and kind of rotation can be obtained right from there. So you can compose these in terms of R and theta, and thereby you can directly write down the numbers depending on how much do you shrink it and how much do you rotate it. Okay. So you can write down the IFS of such an image just by looking at it with hand. Simply use a protractor to find out by how much do you rotate it, that is it. Okay. Let us go to another image. Fine, you know where it is converging to. Good. So in this particular image, how many will you need? Yeah, right in the first iteration you knew that it required 8, right? Good. Such common sense is always handy. How will you make it? Okay, give me just one of the affine transforms. You will need to shrink the square into 1/3 of it in each side, right? So that will be the elementary affine transformation, and then you have to translate them into 8 different places. Okay, so that will not be very difficult for you to do. Let us look at this. Then also you know, right, well, what will you need in this case? As it is happening, you know how many you need, right? Because 1, 2, 3, 4, 5, 6, 5, 7, 8, 9. You need 9 of them. You immediately know. But how do you transform them? How do you obtain the transforms? Can you just look at it and tell me? You will keep rotating by an angle. Now, initially you have to shrink it for the outer ones. You will need to shrink it, translate it, and then keep rotating by an angle. Okay? Clear? And that can be obtained from that r theta kind of structure of this ABCD matrix. So, middle one, yeah, middle one is another one. That means you need a affine transformation for the middle one with a different contractivity factor, right? These ones will have to be contracted by a factor which are the same, but the middle one requires a different contractivity factor. You can see that. So, you will need 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them. Clear? The way it is going, you immediately know, right? Now you need more of the numbers. Okay, you can see that it is converging onto something, right? How many would you need? You need 3 really. You need 3 really, but this is sometimes difficult if you look at the final image only. Now you are seeing it happening. So you know that in each iteration it is really doing it thrice. So you know that it requires 3, but you should develop the ability to look at an image and tell, no, this requires really 3. So that requires some practice. Okay. So what I will ask you to do is to get this practice. Okay. Suppose there is an image where you have a, look at the drawing here. This, imagine that this is there, this kind of structure is there in each of them. So how will you do that? Only this is there, only this is there, and so on and so forth. Suppose you have this as the image that you want to converge on. What will be the structure? The whole thing, you will make one affine transformation to create the middle one. One here, 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 you need 5 of them. Okay. The point is that the moment you have created all the 5, then that information, those numbers are sufficient to create this object out of anything. Okay, out of anything. Good. So after having this much practice, we are in a position to take the next step. Look at the structure of the Kohl's theorem. We said that there is an element of the Hausdorff space L. XD is a complete metric space, so that as we take the steps, we know that we always land in an element of the Hausdorff space. Now, we had defined the transforms, or we wanted to make the transforms in such a way that the transformed things, their union creates a very close resemblance to the original image. And at that stage, we had sort of assumed tacitly that we will apply the W's to the whole image to get parts of it. Is it really required by the theorem? The way we prove the theorem, essentially all you need is to apply some transformation to the image L, but at this stage it does not say anything as to whether you apply, we have to apply it to the whole image or a part of the image. This algorithm was working fine for this kind of images that we have seen, because in these cases the whole is really transforming to the part. But there are many cases where the whole is not really transforming to the part, rather you can get a part from a part. There are self similarity between parts, but not the whole is, not that the whole is transforming into a part. In those cases you can apply the same theorem without any difficulty. So, in this case when you apply the omega n to L, we will only say they will apply the Wn to not L, not the whole set L, but the part of the set L. Then also it is true. Okay. There was nothing in the steps that we followed in order to derive the Kohl's theorem that excluded that possibility. So, that brings a very interesting possibility, that suppose you have some general image, say right now I do not have an image on this, but imagine that on this you have got some kind of image, say some kind of a cloud here, some birds flying here, a tree here, and some whatever it is. I mean, you can imagine any kind of scenery. Now, here we have the clear sky, here we have the cloud, here we have these things. Now, you see the sky, there is a great deal of what is known as affine redundancy in these parts of the image, right. It is not necessary to store all this information related to all the parts of the sky, because in the parts of the sky a part can be obtained by an affine transformation of another part. If that be so, then obviously we can store the image as which part transforms to which part, thereby finally creating this image. Okay. So, how we will go ahead with this kind of algorithm? What we will do is, we need to define a few affine transformations W's, and as we said that in this case the W's will be transforming parts to parts. Say we find that this part of the cloud is quite similar to this part of the cloud, only if you do some affine transformation you get this part. If that be so, then the larger square can be made to transform into the smaller square, not the other way around, because you need contraction mappings. Okay. So, you always have to find some larger area in the image which when affinely transformed gives me a smaller area within the same image. So, in that case, say there is a tree, the tree has some part here, another part there, a larger part here, and then this part can be affined. If you find that this part can be affinely transformed to get a very close resemblance of this part, then the information contained in this part is really redundant. Clear? Similarly, you will find that in most images there is a very large extent of affine redundancy. So, the algorithm that the fractal image compression relies on essentially takes care of this affine redundancy, and tries to find out the minimum information necessary in order to store that image. So, here the idea is what we are dealing with is fractal image compression. You know, the standard way of image compression is discrete cosine transformation, while in this case we go by a completely different logic. There it is the higher order terms that are eliminated, but in this case we essentially talk about the affine redundancies. So, what we will do is we will divide the image into boxes, say a box like this, a box like that, a box like this, and so on and so forth. And then suppose I am trying to find out where the first box comes from. That means we are trying to find out if the information contained in the first box is really necessary or redundant. If it is redundant, then its information must be available by some affine transformation from somewhere else. So, suppose it is this part has to be a larger square from which it comes. That means the original image is divided into smaller boxes, which we try to find from where does this information come, and then we scan the whole image, and then we try to locate, okay, here is a place which when affinely transforms give this image. So, this image, this part, this subset maps to this subset. Okay. These blocks from where this information comes to here are called the domain blocks, and the ones where it maps to are called the range blocks. So, the whole image is divided into the domain blocks and range blocks, and finally we try to find out for each range block where does the information come. Now, you notice that here we have far lesser number of choices, because normally you have seen that you can affinely transform in any possible way, but here since we will be dealing with squares, squares can be only a few ways transformed in order to give another square, right. So, this square can be rotated in all possible angles, can be flipped or can be shrunk. So, these are the possible things, but it cannot be rotated by 45 degrees in order to get this image, right. So, there is only a few number of affine transformations possible that will get from this image, it will get this image. So, the number from which you choose is rather limited in this case. In the earlier cases we had considered an infinite array of possibilities, but here the array of possibilities would be limited. So, you can only check from a array of possibilities which one fits it the best, and find out of the whole image which particular domain block gives me the least housed of distance. Clear? Then you go to the next one, do the same procedure, go to the next one, do the same procedure, and finally when you have scanned the whole image, then what do you need to store? What do you need to store? You need to store that for this particular range block, the source was here, another particular address of the domain block plus the specific affine transformation that was necessary in order to bring it here. Clear? So, you do not need to store the image pixel by pixel, you do not need that. You are dealing with relatively larger, say 8 pixel by 8 pixel kind of blocks, and that we have found that here is a 16 by 16 pixel block from where it comes. So, you need this address, you need this address, and you need the transformation, that is enough. So, at the end of the day, what you are storing is nothing about the birds, nothing about the sky, nothing about the tree, nothing about the grass, nothing. You are only storing some addresses and the transformation necessary to bring this domain block to this range block. Okay. Then, after having done so, you can start from any initial image, and it will always converge into the final image, always. Some questions are obvious. Firstly, so far we have been dealing with binary images. So far we have been dealing only with binary images. That means we are talking only about zeros and ones. Either a particular dot is there or not there. But in actual images, if we are talking in terms of say grayscale images, a particular dot is either there or not there, that is not the situation. There can be grayscale values assigned to each pixel. How to take care of that? In real images there are colors also. How to take care of that? Now the way to we take care of that is, there are a few ways, but one you can imagine this way, that for each one, so far we have been talking about R2 space in which we imagine this. Now you may, for each one, for each pixel there is a additional element to it, that is the grayscale value, and the grayscale value varies from 0 to 256. So you might imagine that as a depth. Okay. So apart from a value, apart from whether it is there or not there, there is also a depth element to it, so that we are essentially dealing now with R3 space. You can do the same thing. There was nothing very special to R2 space that we talked about, right? So we can think in terms of the R3 space. That means there is the x coordinate, y coordinate and a z coordinate, and the z coordinate is nothing but the grayscale value. So this way it is possible to obtain the image, and you can do the same procedure. In terms of colors, what we normally do is, if we can obtain the grayscale image, then the color image is nothing but 4 grayscale images, okay, in 4 of the elementary colors. So essentially if you can store the image in 4 grayscale images, you have got the color image. So the generation of color image is no difficult. Remember, this particular algorithm is successful only in cases where you have great deal of affine redundancy. Otherwise it does compare with other available image compression algorithms like the JPG and MPGs also. Those use the discrete cosine transform. There in particular types of images they perform better, and in some particular types of images the fractal image compression performs better. So at this stage let me show you a few things. For example, here we started with the L, the image of Mona Lisa, right? That is our subset L, and we have obtained the set of affine transformations that will get it there. So we can start from any arbitrary image, which is the middle one, the second one. Can you see the cursor moving? Yes. So this is the starting image for the decompression algorithm, and as we go on applying that, this is the first iterate, this is the 5th iterate, this is the 50th iterate, this is the 250th iterate, and then you can see it is almost the same as the original image, right? So all that has been done in between is, for this particular image, this algorithm has been applied. That means the whole image has been divided into parts, the range blocks, and for each range block an algorithm has been run on it to find out from which particular domain block it brings it there through some affine transformation. From an array of affine transformations, possible affine transformation, a particular one has been chosen which gives the best fit, and thereby we have obtained the whole image. We have codified the whole image, and that code when run on the actual image you get the same image back. Clear? This image may not be all that clear because this is actually a screenshot, that means a actual photograph taken from a computer screen. So let me show this one, which is the Lena image. It's a standard benchmark image used in image compression. So for it also the image compression code was generated, and if you start from a completely black image, you can see this iteration 1, iteration 5, iteration 30, you are almost there, right. Completely white image, again same process, you get the a random image, there also you get, can you see the iteration going? So this one and this one would be different because the initial conditions were different, but ultimately it converges onto the same kind of image. And it started from the parakeet, and that also converged onto the same image, which essentially shows that it is independent of your initial condition, right. I mean, we had a plan once to start from my image to converge onto some good actress, but it did not work out. Okay, so so is it convincing now that it is possible, it's doable, right? If it is doable, then these are all black and white images though, but you easily understand that any colored image can be broken up into 4 black and white images, and you can do the same thing for that. So in the fractals, in the study of fractals, what actually we have done, we have first seen that the natural objects are fractals. Natural objects are fractals in the sense they have complexities within complexities, and at no level of magnification does the complexity cease to exist. So these kind of structures, these kind of objects, this kind of geometrical objects need a different kind of description, and so we found that description, that quantification can be done through the idea of dimension of the object. We have obtained the quantification of the dimension, how to obtain the dimension by what is known as the box counting algorithm. You have done the box counting algorithm where you have a grid of, like a graph paper, put on that particular object, and you count the number of boxes and you put on that algorithm, you get the value. We have also seen that this particular number that you get as the dimension of that object, that not only satisfies your curiosity, but it has physical significance in the sense that in situations where the crookedness, the curvedness, the non-smoothness, these things matter, there that number is a real quantification of the phenomena under consideration. A very glaring example would be the human lungs. So its fractal dimension actually tells the amount of air it can, amount of surface that is exposed to the air, and as the quality of lungs degrades, it has been found that the fractal dimension changes. Okay. The solid catalyst, for example, the amount of surface that is exposed to the reactants, that is dependent on the fractal dimension. So it is not only the material, not only the quantity, not only the surface area, but also the fractal dimension that is important in these cases. We have seen that fractals are important in the study of dynamical systems, in the sense that in a dynamical system we have a state space consisting of the variables, state variables, and in the state space we have initial condition, and then if you have the set of differential equation, then you can evolve the initial condition to get the values at certain points. For certain initial conditions, the state may remain bounded, and for some other initial condition it may go to infinity. So if you plot those initial conditions in the space of in the state space, then you get an object, a geometrical object, whatever it is. In some cases that geometrical object is a fractal object, in some cases it may not be a fractal object. So it is not so that it is always a fractal object. In dynamical systems, the fractal objects also appear in parameter spaces. That means every system has some parameter, and the parameter, if you put two parameters as x coordinate and the y coordinate n, then any point in that parameter space will be a specific choice of parameters. You will find that for certain choices of parameters the system remains bounded or the systems exhibit some kind of behavior. For another choice of parameter it may exhibit either a different kind of behavior or completely unbounded behavior. So, if you now map the parameter space for the particular sets of parameters for the same kind of behavior, then you get a set, right. So, these are the issues that are often misunderstood in studying the fractals, because fractals are beautiful, fractals are nice looking, fractals are good mathematics, all these are fine, but actually they are representative of physical phenomena. So, in physical phenomena you have the state space as well as the parameter space, and the way we have seen that the state space, its representation, a very toy model was given in terms of that z n is equal to z n square plus c, and then we found that you have fractals both in the parameter space as well as the state space. What is it called where it is the fractal in the parameter space? It is the Mandelbrot set. What is it called where it is the fractal in the state space? It is the Julia set. So, when you are studying any dynamical system, you do expect such thing to occur, but they will look different. They will not look like the Mandelbrot set, but always you should remember that there are fractal objects in the state space as well as the parameter space. Then we went on to the generalized method of understanding fractals. That means fractals in general are compact subsets of the underlying space. We had considered the underlying space of R2 space. Compact subsets of that underlying space is basically images. So, we have images, and we said that all possible images, let there be a space where the elements are all possible images. And then after a few very natural steps that are done in any study in functional analysis, we arrived at the conclusion that this space is complete, the space is a metric space, and we succeeded in deriving some transformation that will take a point of the space to another point of the space, meaning an image to an image. A succession of these, a repeated application of these, iteration of these will lead to some kind of image. That led us to the idea of the iterated function system, IFS. Okay. So, what is an IFS? It is essentially a IFS, iterated function system. It is basically taking steps in the Hausdorff space. So, one point to another in the Hausdorff space is a collection of W's, so that from here to here you apply each of these affine transforms to the original set, you get the transformed ones and take the union. So, all that taken together is the iterated function system. Iterate that repeatedly, you always get to some kind of image, so long as the contractivity factor of the iterated function system is less than unity, and that is guaranteed so long as, since these are affine transformation, there is a ABCD matrix if the determinant of that ABCD matrix is less than unity. Very simple. So, you can always set the values so that they are less than unity, and you can always be guaranteed that it will converge onto something. So, it is nice to play around with it. It is nice to simply say, okay, let me choose a particular 3 affine transforms W1, W2, W3, and let us set the values. I know that it is contractive. Now, let us see where it converges. So, I urge you to play around with these things, then that will give you some idea about the relationship between the ultimate image that you get and the kind of affine transforms you started with. Then we have done the idea of the generation of the iterated function system from any object, that can be done for the complete self similar object in a deterministic manner. Complete self similar means where the complete thing, full image, maps to a part as it happens in the found image, as it happens in the tree image, as it happens in the spiral image. So, in those images it is possible to obtain the part from the whole. So, you have a particular type. There are also situations where the parts are obtained from parts of the image. In those cases also you can write down the iterated function system, but you then have to say which part mapped into which part. For the full one you did not need to store the coordinates or the location of the source, because the whole maps to a part. But if you map a part to a part, then obviously you need to store which part comes. Which part means it has some coordinate, some address, so you need to store the address. Obviously when you have a part mapping to a part, that kind of a situation, the contractivity factor or the compression ratio would be smaller, because you are additionally having to store the information about the place from where it comes, right. So, this can be applied to binary images. You can easily do that by simply binarize any of these images. So, you have the Lena image, you have the Mona Lisa image, you have any of the images that you can download from the net, and you binarize it using any of the software that you have. Most of the Windows software that are able to do that. So, you get binary image out of it, and you can apply the same algorithm. It will be very simple to apply the same algorithm on binary images. So, provided you have time and provided you have the playfulness, you write the code to at least do it for binary images. That means to search the image for proper domain blocks which will map into proper range blocks. I am not giving you as an assignment to be done by everybody, but those of you who are enterprising enough to try it out, do try it out. The one where you are really using grayscale images, that is relatively difficult to code because of the third dimension, the depth, relatively difficult. So, I do not think you will be able to do it within this space available for this course, but the binary image is doable thing. And of course, you have the vacation now. If you have a computer, you can always write the code for even the grayscale images. So, that is almost all about fractals. Almost means there are also issues, like these days fractals are used in generation of fractals are used even in interpolation. For example, if you have some data from here to here, and if you are asked to interpolate, what will you do? You will either interpolate by a straight line or by some kind of a spline kind of fit between them, right. You do not have any other way. But if you know that from this point to this point the data is like the share market index, obviously you know that in between it went like this, right. It cannot go like this, it cannot go in like a straight line. So, if you now have 2 points and you want to interpolate, how would you interpolate? Obviously, you cannot interpolate by a straight line or a spline kind of fit, least square kind of fit, you cannot do that. So, in those cases you need a fractal to interpolate this image, right. How to generate those fractals? Yes, there are methodologies for that. There are methodologies to generate surfaces, not only curves but surfaces. For example, if you see a rock surface, if you see a mountain surface, it has a texture, right. How to generate that kind of a texture? So, there are issues involved with generation of that kind of surfaces, which I will not go into, but those of you who are enterprising enough, you can read the books. There are many books that are now available. The elementary book is Michael Bunsley's Fractals Everywhere. Okay. There is also a book by probably fractal geometry or something like that. Okay. So, now you may go ahead with reading these books and further information can be gathered, but for the purpose of this course, that is all. So, this is the extent to which we have covered on fractals in this course. Thank you very much.